Okay, so we are talking about exponential functions today. So sorry for the pause. But chapter 5, what we're going to get to are logarithms. And logarithms and even exponential functions also are super important in not only mathematics, but biology, chemistry, any science really uses exponential functions and logarithms to tell a lot of things. For example, population growth, population decline can all be modeled using exponential functions. I'm going to start saying stuff that I'm not exactly sure, but if I remember from chemistry, like the pH scale, right, is logarithmic, I think. I don't know. So we'll get to that when we start talking about applications of logarithmic functions at the end of this chapter, but exponential functions and graphs. So I want to really make sure that everyone kind of understands that when we talk about exponential functions, so there is a difference between x squared and 2 to the x. This is a polynomial, okay, because we have the x is the base of my exponent of, there's an exponent, but the x is my base and the exponent is the constant or the number. And this right here, 2 to the x, is not a polynomial. 2 to the x is what we call an exponential function. So what I would like to do, what we're going to do, is we're going to look basically at what is an exponential function. We'll talk about kind of its domain and range. Then we'll talk about what does the graph of it look like. That's what we're actually going to start with, is what is the graph of this exponential function. And then finally, we'll talk about some applications, some pretty easy ones where you just kind of plug in numbers and see what happens. Okay, so let's see what the graph of 2 to the x looks like, right? We know what x squared looks like. That's a parabola. That's pretty easy to know, but what about 2 to the x? So just like when you were first learning, when you were just a little toddler when it came to algebra, right? We didn't know what the graph of something looked like. We can build a table. So let's put in some x values, let's spit out some y values. I know you have your calculator, we can just plug them in, but let's see what kind of happens. So think about our domain here. What can we plug in for x? Well, we can plug in anything. So we're going to see our domain is all real numbers. And then what we're going to see here, anytime I raise 2, remember 2 is positive and all of our exponential functions, our base is going to be positive. If I raise that 2 to any number, I'm also going to get a positive number out. So we'll see our range is going to be all positives, domain all reals. So let's put in 0. 2, whoa. 2 to the 0 is 1, right? Anything to the 0 power, remember, is 1. So I'm going to go ahead and plug in 0, 1. And the interesting thing is, for any exponential function then, like even if I had 3 to the x, 4 to the x, if I had 1/7 all to the x power, these all are going to go through the point 0, 1. So they all have the same y-intercept as long as you haven't messed with them at all, right? Like moved them around. So let's just start plugging in some numbers. If I plug in 1, obviously, let's remind ourselves what we're doing here. 2 to the first power is 2. So I'm going to go over to 1 and go up to 2. Okay, and then if I plug in 2, obviously I get 4. Plug in 3 and I get 8, right? So if you notice, this guy grows pretty fast. Some would say it grows exponentially. So when you hear people say, oh, that grew exponentially. Sometimes I annoy people and I'm like, are you sure it grew exponentially? Do you have data to support that? Do you know it grows like an exponential function? Which, I don't know. Maybe that's why I don't always have the most friends. But that's kind of what they mean, right? When people say something grew exponentially, what they mean is it grows really fast. So sorry about this. I'm gonna get out Desmos here pretty soon, I promise. All right, so remember I told you that the domain was all real numbers. So we have some numbers that we haven't even considered. We need to think about negatives. So what does it mean to take 2 to the -1? So remember, a negative exponent just tells me I'm in the wrong place, right? So that's 1 over 2 to the first power. That's what a negative exponent does. So when we put in -1, we get a 1/2. So this is what I'm talking about, my range being positive. Anytime you raise a positive number to an exponent, no matter what that exponent is, you are always going to get a positive number back out. Like 2 to the -2 is 1 over 2 squared. So what is 1 over 2 squared? That's 1/4. And so you can see that this guy grows pretty quickly. In the negative direction, it gets pretty small. So when they say it grows exponentially, you should ask them like, well, do you mean as x goes to infinity or as x goes to minus infinity? Or maybe you shouldn't, and you should keep your friends. That might be a good thing to do also. So as you can see, this is 2 to the x. So 3 to the x, 4 to the x, very, very similar to kind of what 2 to the x would look like. Let's look at some of those if I can pull this up correctly. So here's my 2 to the x. Let's kind of mess around with this and see what happens when I have something like 3 to the x. Well, that was not 3 to the x. 3, excuse me, to the x. So if you notice with this, what's just going to happen is this guy's going to grow more quickly, right? Look at it goes through 0, 1, just like 2 to the x did. But when I put in 1 instead of being at 2, I'm going to be up at 3. When I put in 2 instead of being at 4, I'm going to be at 9. And then if you notice here also, if you see here, it grows more quickly to the x-axis also. So it's going to hug that x-axis a little bit faster. If we did y equals 4 to the x, again, you see the green there, it grows faster than even the other two, and it's going to go even faster here. If I did y equals, 9 to the x, I don't know, it's going to grow faster though. So again, see that purple number there, but depending on my base, it's just going to grow faster. So that's what you can do too to annoy people. Like it grows exponentially, and you can be like, well, what do you mean? What base would it be for exponential? So a lot of ways to make friends as a math nerd. All right, so that's kind of neat. What I want to talk about now is, okay, so you're probably like, well, that's great, Sarah. I'm sure that's what you're always thinking when you watch my videos. But what if my base wasn't a nice whole number like you keep using? What if I had a different base that was not a whole integer? So let's talk about like this 1/7 here. What would happen if we had 1/2 to the x? And I'm going to tell you whether you like it or not. I'm going to tell you. So let's look. Oh, wow. But I'm going to get a different. Sorry about that. I'm going to get a different tip size here for my pen. So let's talk about what would happen if I had 1/2 to the x. So I didn't have a whole number. Let's see what's going to happen here. So again, if x is 0, I still get 1. Okay, I'm still going to go through that 0, 1 y-intercept. Okay, this is going to be fun. You guys are going to really like this. Look at what happens if I plug in 1. I get 1/2 to the first power, which is 1/2. So now instead of being at 1, 2, I'm at 1 1/2. Well, look at that. Isn't that crazy? Let's look at what happens when I plug in 2. I'm going to get, 1/2 raised to the second power. So that's 1/2 times 1/2, which is 1/4, right? So I'm going to have at 2, I'm going to be at a 4th. At 3, I'm going to be at a 3rd. So this guy is going to kind of hug that x-axis really close, just like 2 to the x did, but on the other side. And now what's cool about this one is if I plug in a -1, look what I have. I have 1/2 to the -1. What does a negative exponent do to a fraction? It flips it. Remember that negative says I'm in the wrong place. I'm in the wrong place. So it's going to take that 1/2, it's going to flip it, and then the 1 becomes positive. So now I get 2. So notice what this guy does. At -1, I'm actually up at 2. Okay, excited? Let's try -2. 1/2 to the -2, if you remember your properties of exponents, and who doesn't, right? I flip that 1/2, that's what the negative does, and then it's raised to a +2 now, and so I get 4. So at a -2, I'm actually up at 4. Likewise, at a -3, I'm going to be up at 8. And so what I get is this really cool looking exponential function that instead of increasing like my other one did, this is a horrible graph I saw. I'm really, really sorry for that. Instead of increasing like my other one did, I actually am decreasing. Remember our other one went through really quick. I'm just going to graph this. I should have left it up there. Remember what our other one did? 2 to the x, right? Looked like this. Okay, and oh, that's really, really bad. So 2 to the x look like this. What do you notice about these two functions? I'm pretending like you're responding to me. That's right, my friends. They are just reflections about the y-axis. And the way that you can kind of see that is if I have 1/2 to the x. Well, 1/2 is the same as 2 to the -1, right? Raised to the x. And everybody knows, everyone's talking about it. When we raise an exponent to an exponent, we multiply those exponents. So notice we have 2 to the -x, and this is 2 to the x. This guy, my friends, just like we noticed when we talked about transformations, this is just a reflection about the y-axis because of that negative in front of the x value, right? Remember f of a -x was just a reflection about the y-axis. So pretty cool. We can see also this is going to be true with any number that is between 0 and 1. So it doesn't just have to be, 1/2, 1/3, 1/4. I mean, it can be. So I can do 1/2. And I just really messed that up. Whoa. Oh, Desmos, you know me too well. You're already putting in my exponent. So there's my 1/2 to the x. It's decreasing, unlike 2 to the x, which was kind of increasing, right? This is good, and the same thing here that we would think would happen if I did 1/3, this guy is just going to like decrease more quickly, right? Or have a steeper kind of slope up here. But again, it doesn't just have to be like 1/3, 1/4, any number between 0 and 1. So like 3/4, right? Which isn't as easy to think about as like a reflection. It'd be a reflection of 4/3. So that's not as easy to think about. But even if I did 3/4 to the x, and I should put an equal sign, and look at that one, that's kind of cool because it doesn't, it's closer to 1, so it's not going to have quite that same shape. Why am I not getting a cool color for that? That's interesting. Apparently Desmos does not like the fractions. Or like 1/10, if I had 1/10, I'm not as close to 1. I should get one that's going to, yeah, look at that blue. That's going to decrease pretty quickly. And as you notice here, get really, really close to the x-axis quickly. Because if you put in 1, if you think about that, here's 1. 1/10 to the 1 is already 1/10. 1/10 to the 2 is 1/100th, so it's going to go pretty fast. So I hope that makes sense. Some interesting things about this: these functions are always increasing or decreasing depending on which one you're looking at. If you're looking at a number bigger than 1 as your base or less than 1. So let's write down a couple of things about these functions that are going to be interesting to us. I mean, everything's interesting, right? Oh, I always do that. Oh, I get it. I understand. Let's talk about some things that are going to be interesting to us, and let's actually write down what an exponential function is, because that would probably be a good thing. So, all right. So an exponential function. So some things that we are going to assume, or not assume, but something that we know when we talk about an exponential function. So this is sort of like a definition. So the function. And it is a function. You saw it pass the vertical line test. For every input, there's one and only one output. So an exponential function, kind of the general form for it, we say is a to the x, where x is a real number. So I'm going to use a little bit of, I'm being lazy today, but x is a real number, right? Element of the real numbers. Couple things about a. A must be greater than 0. A cannot be 1. Because if it's just 1 to the x, that's boring. That's just a horizontal line, 1. This is called the exponential function base a. Okay. So when we talk about an exponential function, we can talk about its base, and we know kind of the general shape of any a to the x, right? Couple things about this guy. What do we know about its domain? Well, we said that x just had to be a real number, so its domain is going to be -infinity to infinity. Its range for both of these, whether it's increasing or decreasing, look at, we haven't messed with this at all. To give you a hint about what's happening, gonna happen eventually, is 0 to infinity, never equals 0. I can't ever raise a number that's not 0 to any other number and get 0 back out. What's some other things? So if a is greater than 0, we're going to be increasing everywhere, increasing from -infinity to infinity, not greater than 0. Oh, Sarah, come on. Greater than 1. Excuse me. Again, how embarrassing. Greater than 1, we're increasing everywhere. If a is between 0 and 1, meaning now every number is a fraction, right? So I don't want to say like if it's a fraction, but if it's a fraction between 0 and 1, we are decreasing everywhere. Decreasing from minus infinity to, and again, this is if I haven't messed with it, which means you can see what's gonna eventually happen with this, right? I'm going to mess with it. So that's kind of some interesting stuff about the exponential function a to the x. And I encourage you, when someone says that if something grows exponentially, to challenge them to tell you what the base is, right? Okay, so let's mess with these a little bit. I'm going to go back to Desmos, and we're going to write down some stuff here and figure out what's going to happen if I kind of mess with these. So if I start with my 2 to the x, so my y equals 2, right, to the x. I have this nice exponential function. It's increasing everywhere. Oh, green's my favorite color even. What a good day. What do you think would happen if I added 1 to this? So I'm not going to actually put this graph on yet, but what if we did y equals 2 to the x, okay, and then I want to add 1. So if I add 1 to it, now you guys should have like kind of an idea of what's going to happen to that. Just like if we added 1 to x squared, it's going to shift it up 1. You are absolutely right. It's going to take that graph because it's adding 1 to every y value, and it's just going to shift it up 1. Okay, I hope that makes sense. So when I have you graph these, I'll ask you again to do kind of a simple sketch. I want to see one point you know it goes through, and that's usually going to be this point right here. So notice how we had the point 0, 1 that all of the kind of base parent functions go through. It's just going to be shifted up 1. All right, people, what if we added that 1 to the x value instead of to the function itself? What is that going to do? Sorry, you might hear some of my kids in the background because I'm, oh, sorry, I don't know why. This isn't letting me, it's not letting me. Let's try this again. X plus 1. Oh, come on. All right, so let's think about what is going to happen. Let's use some parentheses. There we go. They like that better. What's happening if I add this 1 now to the exponent as opposed to the function itself? So if you notice, it kind of looks like it shifted it up 1 again. It actually doesn't. So here's my original function. Notice this point right here, this 4, is not being shifted up 1 to 5. What this is going to do, and this should make sense to you as well, is it's going to shift it to the left 1. Just like we saw with our functions, like if I added the 1 to the x, when I had x squared, it would shift it to the left. That's exactly what's going to happen here. And then, of course, if we keep looking at this, if I put a negative in front of it, just like we would think with, you know, if I put a negative in front of x squared, that flipped my parabola. That's going to be a reflection about the x-axis. And again, this point right here is going to be reflected over now, and we have 0, 1. And we can do things, you know, we can get crazy and do stuff like this. So for example, this one right here, what has happened now? Order of operations kind of matters here. We have reflected it, right, with this negative right here. We've reflected it about the x-axis, and then it's been shifted up 1. So look at here, there's my reflection about the x-axis, there's my 0, negative 1, and now this purple guy right here is going to be shifted up 1. You can put this on your calculator, you can use Desmos. I'm going to have you graph these, but again, you're welcome to use your calculator and verify. So let me kind of show you the stuff that I want you to do. What I'm going to do is I'm going to give you, well, I'm going to show you right now. Let's do some examples. Okay. Someday, after I've been doing this for like 17 years, I'm going to remember to not edit a layer that is not selected. So let's look at a quick example. So what I want us to do is I want us to state the parent function. Okay, state the parent function, all transformations, and sketch a graph. And sketch. Okay, so I actually might bring in my guy here. So let's look at a equals, so let's say we have something like y equals 3 to the x minus 2. So what I want you to think about here, well, let's you know, answer the question really quick first. All right. So first, what did I ask for? The parent function. So what is the parent function here? The parent function that we're going to have is just 3 raised to the x value. And then this minus 2, because it's with the x, is going to go to the right 2, right? So what I like to do is I like to kind of think about, I know 3 to the x itself, right, goes through 0, 1, and I know at 1 it goes up to 3, and it's going to kind of go like this. So I'm just going to kind of graph my parent function, what I know it's going to kind of look like. I usually have to graph my parent function to be able to do these transformations. Not always, but some. So I'm going to take this guy and I'm literally just going to move everything to the right 2. 1, 2. So at 4, right, I'm going to be up at 9. And you could plug in numbers if you wanted to. Hopefully you'll get to where you don't have to. But here is where my graph, oh no, sorry about that, it's going to look. And mainly what I'm going to ask you for is I'm going to ask you what happens to that point right there, right? That point, sorry, that should go through 0, 1. That point right there is shifted over 2. I hope that kind of makes sense. Let's look at another one. And you can look in Desmos, you can check this, of course, on your calculator. I encourage you to do so. So what about something like this? Y equals 1 minus 2 to the x, okay? So my parent function here is going to be 2 to the x, okay? And what I'm going to do is I'm going to rewrite this really quick to negative 2 to the x plus 1 to kind of see what I'm going to do here. I know this guy's going to go up 1, and then what does that negative do again? So let's actually, I'm sorry, let me do this in the order in which this occurs. What's going to happen first? We're going to reflect about the x-axis. And then what's going to happen after that, we're going to go up 1. Those are the transformations that are going to occur. So again, 2 to the x, I'm just going to plug in a couple numbers. I don't have to have all of them, but sometimes I get a little freaky and want to graph more. So I know my graph is going to go kind of like this. That wasn't so bad. And so this guy's going to go kind of in stages, right? So I'm going to reflect. So I know all of these points now. That guy is going to come down here. We're going to be a reflection. I see it. I see it. I see it. I see it. Okay, it's going to be a reflection, right? So I know that I'm going to have this guy, and we did this one on Desmos, but now, so let's get rid of that parent function. So I've had that reflection, okay? Now what am I going to do with that guy, right? I'm going to go up 1. So now my final answer then, let me get kind of, ooh, pink, is I'm going to move all of these points right here. I'm going to move them up 1. So this guy, instead of getting really, really close to the x-axis, what it's actually going to get really, really close to is 1. So that guy's going to move up 1, and we're going to get something like this, okay? I hope that makes sense. So what I'm going to look for again is for you to just do kind of a simple sketch of it. I want to see a couple points you go through, maybe even just one point, but then, you know, get that general behavior of the function and make sure I can kind of see what is happening. Let's do one more. This lecture is not going to be super long. And then I want to look at like one example of compounding interest, and then we'll call it good. So let me find one that's maybe a little bit more interesting than what we've done. And you can like stretch these just like we did before. You can have like crazy ones like 3 times 2 to the x plus 5. This would be a shift up 5. This would stretch it by 3 just like before. You cannot take that 3 times the 2. Don't you dare. Don't you dare do that. Do not take the 3 times the 2 because that's being raised to the exponent, right? So you can't do that. Anyway, you know that though. You would never do that and make your math teacher cry. Why would you want to make your math teacher cry? You wouldn't want to make your math teacher cry. How about 1/3 to the, I don't know, x minus 1 all plus 2. I don't know what's going to happen here, but let's try it. All right, so let's state the parent function. So in this case, the parent function is the 1/3 to the x, okay? Oh, or we could think of this actually as 3. This actually could be a reflection. I guess you could argue it could be 3 to the x reflected about the y-axis, but parent function is 1/3 to the x. That's fine. What are we doing first? We're going to go to the right one. This one actually doesn't really matter which one you do first, and then up 2. I don't think. Maybe I should be careful about saying stuff before. I think of stuff before I say it. Okay, I'm going to graph my 1/3 to the x. So I know it goes through 0, 1. At 1, at 1 I'm at 1/3. At -1 I'm actually up at 3. At -2 I'm up at 9. And then remember this guy kind of gets close to the x-axis as we go to infinity. Okay, so it has a horizontal asymptote at the x-axis. All right, so let's see what's going to happen here. So I am going to go to the right one. So I'm going to go right one. So what's going to happen is I had my brush size. So I'm going to go to the right one. All of these are going to the right one. Okay, so this is what my new reflection is when I'm talking about going to the right one, and then I want to go up 2. So let's see what happens here. So, and then I want to go up 2. So this guy's come over here, and now I want to go up 2. So we're going to be there. This guy I want to go up 2. And now instead of having my kind of asymptote at 0, right, it's actually shifted up 2. So we kind of have this new, not kind of, we do have a new horizontal asymptote of 2. So this pink one, and I'm going to go up 2 on that one. This pink one is going to be my final answer. Again, you can use decimals, you can use your calculator to kind of see that that is true. But these are a little trickier. You know, I can graph an x squared at the drop of a hat. The exponential function, I usually have to kind of, just like I showed you there, kind of think that through a little bit. Okay. All right, let's talk about some applications, and then we're gonna call it good. Oh, the other thing well, let's talk about an application, and then I promise we'll get back to what I was going to say. So some applications. One application is this idea of compound interest. And you may have seen this, you know, in another math class, or we teach it in our problem-solving classes on campus. But the idea of compound interest is this idea of putting money into an account and earning interest on that money, and that interest being applied to not only the money you initially invested, but also to the money that you are earning through the interest. And this is actually a really cool kind of equation to derive. I'm not going to do that for you now. I just don't maybe think it's pertinent right now, but we'll probably look at it as I think in 5.6 we look at something like this, and it's actually a pretty interesting equation for how you derive this. But let's look at this right now, and this couple things here that I want to point out, and you've probably seen this equation before, but A is the amount in the account. Sometimes that's called future value, like that'll be the future value of your account after so much time. But what I usually think of it as is I think of it as accumulated amount. They don't say anything, they just say A, but I'm just going to call this accumulated amount. Accumulated, I don't know if that's spelled right. So this is my accumulated amount. P is the principal. P is the amount of money that you're going to actually invest into an account. We're going to talk about investing. I guess you could talk about interest paid on a loan, but this is called your principal. Okay. R is going to be your annual interest rate. Okay. N is going to be the number of times that you compound per year, okay? So maybe usually it's compounded monthly, like at the end of each month, they're going to put in a part of that interest rate. And that's why we take this R divided by N. If you have like a 12% interest rate and you're compounding monthly, then you take that 12 and divide it by 12, and you would apply 1%. Each month. So it's taking that percentage rate and it's dividing it over the number of times that you're compounding in the year. And then T is the number of years. So that's the time in the account. Okay. So I'm going to be a little bit lazy here because I actually don't have a calculator with me, and my children are out in the living room, and if they see me, it'll be, oh my goodness, Sarah. It'll all be over. So I'm going to be a bit lazy, and I'm just going to use the example that's in your book so that I get the right numbers. Which I usually don't like to do that, but that's okay. So let's look at an example. So suppose this is a high roller example. Suppose $100,000 is invested Okay, at 6.5% interest, compounded semi-annually, okay? So that's going to be the key as to what n is. So like if it says monthly, n will be 12. If it says yearly, n is 1. If it says semi-annually, that means n is 2. That's twice a year. If it says daily, it's usually 365, although in business, sometimes they use 360 because it's an easier number to divide by and stuff. But for now, I think we'll just use 365. So find a function. So part A, find a function for the amount in the account. The amount in the account after 2 years. Okay, so that's just gonna go back to that kind of formula I gave you right there, and I'll give you that formula. You don't have to memorize that, but you'll probably end up memorizing it whether you want to or not. But it's 1 plus p times 1 plus r over n, all raised to the nt. So the function that we're going to find here is just a equals, we're just going to plug in our numbers. So 100,000 times 1 plus, remember any interest rate or any percentage at all that you use in an equation, you need to make sure you write it as a decimal. So remember percentage, right, written as a decimal. You just move it to the left too. And if we figure out what that number is, here we get this formula, A equals 100,000, right, times 1.0325 to the 2t. Hey guys, you know what's so weird about this? What is so weird about this? This is an exponential function. Strange that in the exponential function section we found an application with an exponential function. That's why it's in here. Okay, so this is my formula. So let's find the amount in the account. In the account, we'll just do a couple of these. These are pretty easy. After 0 and I'm not going to do 0. 0 is pretty obvious. When you raise that to the 0, you get 1, right? So let's say after 4 and 8 years. So this is exactly what it's going to look like for how much money we have after 4 years. I'm just going to take this sucker, this exponential function. This money does grow exponentially. And I'm going to raise it to the 2 times 4. Now, obviously, we know what 2 times 4 is. It's 8. When you put this into your calculator, it's quite important that if your calculator does not throw this guy up into the exponent, that you put parentheses around it in case this is not such an easy number as 8. Again, remember, what does order of operations do? It takes this number, it raises it to the 8th power, and then it multiplies it by 100,000. And if you do that after 4 years, we get about 129,157. You should put this into your calculator and see if you get what I get and 75 cents, which is pretty cool. So what that says is, how much money did we make after 4 years? We didn't make the whole 129,000. We had to pony up that 100,000 to begin with, but we made about $20,000, right? And after 8 years, you're going to do the same thing. A of 8, you're going to plug in 8 for t, and it looks like after 8 years, we have about $166,817. And again, take your calculator out, try that, see if that's what you get. Okay, I hope that kind of makes sense. There's a lot of things we can do with this. We're going to look at this more when we get to 5.6, I believe, and we'll look at like how we can, well, we will, because we're going to have logarithms. But if we want to know like, oh, well, what's the interest rate that I would need to get this, or stuff like that, we would need to be able to do a logarithm. Like if I want to know how much time would I need to put it in the account for this amount of money to grow to 200,000. Lots of good stuff that you can do there. All right, you guys, the last thing that I would like to talk with you about, so I'm going to, if you're still here, is a number that is one of my favorite numbers, and that is called the number E. I know that sounds weird that we're saying it's a number, but I'm sure you guys have seen the number E, or your friends that, you've been at a party, and you just start talking about the number E. So here's what E is. E is an irrational number. So just like pi, it goes on forever and it never stops. 2.7182828459045. I'm not even looking at anything. Are you guys impressed or what? Yes, I know. I know you thought I was really cool, and then now you just realize that I'm even cooler than you thought, because I know e to the 15th decimal place. If you want to know how I know that sometime, just, I don't know, come find me or send me an email, and I'll show you how I learned that in high school, and I remember that from now on. But so what's cool about e, this is Euler's number. I actually don't think the e is because Euler's name starts with, oh, there we go. That's better. Sorry about that. Starts with an E, but this is Euler's number, and apparently in 1741 he named this number E. So you've probably seen this before. It's used a lot in like biology, and we're going to use it a lot. But one thing that this kind of has to do with is, like, suppose I invested $1 at 100% interest, which I know that's kind of stupid, but 100% interest, right, for 1 year. If you actually, and I encourage you to do this, if you try and make as much money as you can off that $1, right, just by compounding. So let's say you compound like every minute. Let's say you compound every second. Let's say you compound every millisecond in a year. What's going to happen is you're going to see that as n approaches infinity, the amount of money you're going to make, you actually cannot make as much money as you want to. There is a limit to it. As n goes to infinity, actually a goes to e, which is really kind of creepy. It just kind of shows you the beauty of mathematics, but e is a pretty interesting number, and we'll talk about that later on. We'll talk about compounding continuously, which banks will actually do because there is a limit to it, right? We get to E. This says that I can't make as much money as I want by compounding a bunch of times a year. That's basically what that's saying. This guy is an exponential function just like the others. That's going to grow just like the other ones, right? And we can mess around with it, right? It's still going to go through 0, 1. When we put in 1, it's going to be some number kind of between 2 and 3, a little bit closer to 3, and it's going to just grow like that, right? And we can do things to it. If we did e to the x plus 1, this would just shift it to the left 1. If we did e to the x minus 3, that's just going to take this guy and shift it down 3, just like everything we've talked about. So I'm at 37 minutes now. I bet you're about done listening to me. But number e is really, really cool. You have this guy on your calculator. You might have to look for the natural log button, the ln button, and it's probably like e raised to the x or whatever, but look for that on your calculator and finding, we're going to work with e quite a bit, and we're going to talk about its inverse function quite a bit as well. All right, guys, as always, let me know if you have any questions.